let's get started. I think everybody in this room was in the last class, so I'm not going to repeat everything that I talked about last time. I know that there's a couple people in steel who are not in concrete, and so all I'll say is I did the same thing with the attendance grades in steel that I did in concrete. So from here on out, everybody's here, whether you're here or not, so everybody has 100 on their attendance grade from here on out. Doesn't mean previous absences were forgiven, just everything from here on out. You do still have a homework due on Monday. If we have cancellations coming in the near future, we will figure out a way for you all to turn that in. I'm planning to still have the exam Wednesday. The only thing I'll say about that is this: if for some reason we cancel class next week, which is possible, I don't know, we are still going to do the exam next week. There's a possibility I have to maybe move it to Thursday or Friday, but I'll do my best to try and still do it on Wednesday, and we'll just do it online. I'll have an online timed quiz. You all will submit your calculation sheets, scan PDF, and I'll probably give you more time because of the technical stuff associated with it. I don't know. We'll see. But we keep on trucking as of now. But the one thing I did go ahead and do is just give everybody 100 on attendance. I'm just not going to take attendance for the rest of the semester. Okay. So, any questions? You do still have a homework assignment to do on Monday. Okay. I have a lot of stuff here on the board. And I kind of want to take some time and digest it. So let's just sort of get right into it. Let's talk about compression members, specifically their capacity. Now, we talked last time about this. This is Euler buckling, or the elastic buckling stress. And we talked last time about how to derive that expression using differential equations, the assumptions that were made, and so on and so forth. Now, that equation is fine, except for the fact that there are two real-life issues that happen when we're looking at the behavior of a real-life steel shape. The first is the presence of geometric imperfections, the fact that this thing is not perfectly straight or perfectly plumb, and the fact that residual stresses are present from the rolling process. So geometric imperfections and residual stresses make this expression inaccurate, or not good enough to predict the capacity of a wide flame section in compression. So what we do in AISC is we use this. Okay, so I want to explain what's going on this chart. So what I'm plotting here on this chart is a function. So this graph here is plotting the critical buckling stress as a function of the slenderness. Now, one of the things you'll notice is that the code calls this L sub C over R. That's the same thing as KL over R. So those are the same thing. Okay. Now, you have two equations that are used to compute or to plot this curve. So I'm looking at this curve right here. So whenever your slenderness is less than this value, you are predicting your capacity using this expression. And whenever your slenderness is over this value, you're using this expression. And so the idea is that so let's say we're talking about this column. If the column was sufficiently short, we would be able to buckle this thing inelastically. And inelastic buckling capacity would be predicted by this expression. This is the critical buckling stress. But if as the column gets longer and longer and longer, it gets more slender. And as columns get slender, they get weaker. And you get to a point where once the column gets too slender, it can no longer reach that inelastic buckling capacity, and it's governed only by its elastic capacity. So this is the way that we compute this. We say that our critical buckling stress is computed using this expression if our slenderness is less than or equal to this limit, and it's computed using this value if our slenderness is greater than this limit. Now, how do you come up with this limit? You literally just set these two expressions equal to one another and solve for KL over R. That's all it is. So if you set those equal to each other and solve for KL over R, you get 4.71 times the square root of V over Fy. Now, what's going on here is, okay, if I have elastic buckling, you would think that I could use this equation, but I'm not using this equation. I'm using 0.877 times that equation. So why am I reducing it? I'm reducing it because as the column gets longer and longer and longer, the presence of geometric imperfections become more and more pronounced. So if you have a really, really slender column, you got to bump this capacity down by a bit to account for geometric imperfections. This expression here up top, that accounts for all of the residual stresses and inelastic behavior. Okay? Now, one thing I want to make sure everybody's clear on from a mathematical perspective is that this 0.658 raised to the Fy over Fe, this Fy over Fe is an exponent. It is not a fraction multiplier. Okay? So it is not. So what you do not do is say 0.658 times Fy over Fe. That is wrong. What you do is 0.658 and it is raised to that fraction. So that fraction is an exponent. Okay? So just so everybody's clear on that. That is not, you don't multiply by that fraction, you raise it by that fraction. Okay? Another thing to keep in mind, elastic buckling, notice how the expression for elastic buckling, this right here, has nothing to do with the yield stress. The yield stress only matters when you're in inelastic range, because if you're in the inelastic range, you're talking about yielding. And so yielding, or the yield stress, would only matter if you're talking about inelastic. Inelastic range, it doesn't matter. Make sense? Okay. Now, so how do we compute the capacity? The capacity is computed by taking phi times FCR times AG, so it's the gross area times the critical buckling stress times the phi value 0.9. So this is our critical buckling stress, that would be in KSI. This is the elastic buckling stress, which would also be in KSI. So our critical buckling stress is determined by figuring out whether or not we're in inelastic or elastic buckling range, and also by determining the slenderness of the column. Okay? So keep in mind, we have to determine this KL over R. KL over R, keep in mind, the R is the radius of gyration. The radius of gyration, when you typically look that up in the manual, is measured in inches. But when we're talking about member length is in feet. L over R must be unitless. So pay attention to your units when you're computing your slenderness. Okay? So E, the other term, E is the Young's modulus, or the elastic modulus for steel. Young's modulus, E is 29,000 KSI. Fy is whatever the yield stress is for the grade that you're looking at. And then L over R, or the LC over R is just KL over R, which is your slenderness. Now, one other final point I will mention. The expressions that I'm showing you right here, the equations that we're looking at, all assume doubly symmetric behavior. And all of the limits that we're going to look at later all look at wide flanges. The long and short of what I'm saying is that for now, until the rest of the semester, we're only looking at W shapes. No angles, no channels, none of that. Okay? Because we're talking about beams and columns and buildings. And beams and columns and buildings, this is probably one of the most common elements that you use. Except if you're designing a dorm facility from last. Okay, inside joke. All right, everybody good so far? Now, where am I getting these expressions? I want everybody to make sure that you recognize this. I want everybody to open to chapter E. So I'm on 16.1, let's say 16.1-33. Let's start there. Everybody brought their AISC 15th edition steel construction manual, right? Hey, how's it going? All right, don't worry, I'll let you use this here in a second. Okay, if you go to chapter E, what is the title of chapter E? Design of members for compression. Turn the page back, like back a couple pages, and you'll be in chapter D, which is the design of members for tension, and you should recognize that chapter because we used that a little bit ago when we were looking at tension members. So now we're in the compression member section. So if you go to chapter E, the very first page will tell you sort of the organization of the chapter, and it will tell you the phi value to be used is 0.9, and that's actually the case regardless of what you're talking about. Now I want everybody to turn the page one time to the next page. Now what you should be seeing here is this table user note E1.1. Does everybody see that?
There you go.
There you go. They're right there on 16.1-34. Okay, now let me explain that table because I think that's kind of important. What you're seeing there is a table that helps you as the user of the manual identify, helps you identify what section of the manual you need to use for which shape. So the reason why you have different sections is because different equations map the behavior of those different sections a little bit better. For instance, there are different expressions to compute the compressive capacity of a pipe or a square or rectangular tube. Angles and T-shapes kind of have a tendency to want to twist when they're loaded, so flexural torsional buckling becomes an issue there. But what we're going to be looking at is steel eye sections. So the very first one. And if you notice what it says is, there. Now look at the next columns. It says, what is it? Without slender elements, and then with slender elements. Everybody see that? That might not make a whole lot of sense right now. It's about to very soon. But if you notice, it says like E3 and E4, right? And then it says the limit states. And then it also says E7 for the with slender elements. Does everybody see that? So what's going on with that is this. Whenever you have an eye shape, you need to use either the equations presented in section E3 or the equations presented in section E4. Now what's the title of section E3 over there on the next page? It says flexural buckling of members without slender elements. Does everybody see that? Now if you look at the expressions, does it look familiar? That's everything we've just been talking about. Okay? Now the section E4 considers torsional buckling, but that really only becomes an issue when you're dealing with like plate sections or built up elements. Since we're dealing with rolled shapes where everything's symmetric and sufficiently compact, we don't have to worry about that. Okay? So we only need to concern ourselves with E3 really for the purposes of what we're doing in here. Hence why you've got all of this. But what I have yet to explain is what's going on with this E7 and like what's a slender element. Okay? In order to define that, I need to talk about local buckling. Okay? So let me explain what local buckling is. Okay? Local buckling is when, okay, so here's my little rubber mock-up, right? Rubber I-beam mock-up. Take the thing and I load it in compression. I load it and the whole thing bows out. This would be what's called a global buckling mode. The entire cross-section deviates from the axis, deviates from the longitudinal axis and just bows out. That is global buckling. Local buckling defines a buckling mode where instead of the entire cross-section buckling, only a component of it does. Like maybe the flange crinkles or the web crinkles. Okay? And so these would be a couple of examples of local buckling. I've cheated on this one a little bit because it's from a fire that took place in England, but you can kind of see it's not like the whole column is busting out. It's that these flanges are kind of crinkling. Does that make sense? So the way that we, here's what we're sort of after is if we're considering local buckling, we're sort of asking ourselves, does the section look like this? Or does the section look like this? So the section here on the right, we would say that this section has slender elements. I think for some reason with this monitor, when you get to the top right, it's like the pen gets all weird, I don't know. This section we would say is without slender elements, and in steel land, sometimes we call that a compact section. So maybe compact elements. So that's sort of what I mean is the difference between a section with slender elements and a section without. Now, what's the limit? Well, spoiler alert, that's the limit, but I want to show you where we come up with that here in a second. Now, but before I do, just to show you some real-life examples, I'm curious. This is from a fire that took place in London, but this one is a real life example actually here in America. And if you look, you can kind of see the column, like the column kind of bowed out a little bit, but you can also see, kind of see how the flange kind of crinkled here a little bit. So this is an example of local buckling. I'm curious if anybody knows where this is. Well, I'll give you a hint. It's a subway. Chicago. It's in New York. And where do you think this is in New York? It was under the World Trade Center. This was the subway. This was a column failure of a subway support element under where the World Trade Center disaster happened. So, yeah, this stuff happens in real life. I have tried to find a better picture of that. I can't really find a better picture of that column failure, but if you happen to find one, let me know. Okay, now let me explain how you derive the elements or derive these limits. You don't have to follow along with this. Don't worry. This math gets a little out there, so just you can sort of movie time this one a bit. Now, this expression here, this is the expression for the buckling of a beam. Okay, this is us deriving the buckling load for a beam. Okay, this expression here is sort of the equivalent to that, but this is looking at the buckling of a plate element. Buckling of plates and plate analysis is definitely not something that undergrads would be required to do. That is totally a grad school concept. But plate buckling, because it's like partial differential equations, you have equations with respect to x and y, it gets a little involved. But suffice it to say, this is the load that would cause a plate to buckle. And it's a function of a couple things. So we still have the pi squared e, okay? We got this term here, which you actually should have seen this term before. This is what's called Poisson's ratio. Does anybody remember Poisson's ratio from deformables? It's like if I take like a piece of taffy and I stretch it, well, it gets longer, but it also gets thinner, right? And so the relationship between how much thinner it gets versus how long it gets is Poisson's ratio. So each material has a unique Poisson's ratio. The Poisson's ratio for steel is about 0.3. Okay, in fact, the manual tells you to take 0.3 to be Poisson's ratio. And it's also a function of your width to thickness of your plate. So the plate is B wide and T tall. So this B over T is sort of a measure of the slenderness of that plate. Now this is sort of your critical buckling factor. It's kind of like your K factor, but not really. If you start tweaking your plate slenderness, as well as your boundary conditions, like is the plate simply supported, is it fixed, is it clamped, is it free on one end, is it fixed on one end, you start getting different values of K. This is like a grad school project if you ever wanted to try this out. And so what you can do is you can solve for K values, assuming whether or not like one end is fixed and one end is free, or both ends are simply supported, both ends are fixed. And the reason why that's relevant is because you do two things. The first thing you do is you take this equation, rearrange it a bit to solve for this. Then you ask yourself, okay, let me skip ahead a little bit because I don't want to bog you down with the math. So the first thing you do is you solve for the B over T ratio that will cause buckling, and then you ask yourself, well, if I'm looking at an I shape, what is the appropriate K value? Now the way that we handle this in the spec is we split this up between what are called stiffened elements and unstiffened elements. So a stiffened element in like an I shape would be like the web, whereas an unstiffened element would be something like the flange. And the reason why we say that is because if we're trying to figure out whether this thing's going to buckle on its own or this thing's going to buckle on its own, well, we call this a stiffened element because it's supported on two sides, whereas the flange is really only supported on one side. The other side's hanging out in space. Now, I've got different K values as to whether or not these two ends are fixed, these two ends are pinned. You know, maybe this is fixed, that's free, maybe this is pinned, that's free. And so the final decision that you have to figure out is, well, what am I going to do here? Like, let me ask you this. Is that a fixed support? Is that a pinned support? Probably neither. It's probably somewhere in between. So what we do in the spec is we say, okay, let's take this and say it's about somewhere between fixed and pinned. So we pick a K value that makes sense, plug and chug, and here's what we get. So these limits that you're going to see here in the spec, that's where they come up with. We just look at it as if it's a plate, We limited its buckling stress to Fy. We solved for the B over T ratio that would cause that, and there you go. I don't want to bog you down with the math. I just want to sort of keep it straightforward. I want everybody to turn to 16.1-17, which, by the way, if you look here on the board, you see this little section here where I say manual tabs. I have a number of sections that I think you should tab for columns. Now, if you look at 16.1-17,
No, go back a bit. Right there.
you should see a table that looks like this. It should say B41A. Now, look at the title of that table. What's the title of that table say? It says width to thickness ratios, and it says members subjected to axial compression. Now, just for giggles, turn the page. What does the page, what does the next one say? For B41B. It says members subjected to what? Flexure, right? So here's the long and short of it. B41A, that's the table that we use for columns. B41B is the table that we use for beams. Okay? So we'll be using B41B later. Okay? Now, if you look on the left of that table for B41A, back page. Other way. right there. So if you look there on the very, very left, the text is sort of tilted. You should see where it says unstiffened elements and see where it says stiffened elements. Y'all kind of see what's going on there? Now, what we have here is we're looking at unstiffened elements and stiffened elements. So if you look at case, 1 through 4, those are the cases associated with unstiffened elements, and the images over there on the right sort of illustrate all the cases that we would be looking at. So for instance, if you're looking at, case 3? Case 3 is looking at angles, like case 4 is looking at T-shapes, right? We're not looking at any of that, we're looking at case 1. Case 1 is the flanges of rolled eye shapes and whatnot. So what we have here in that blue box is we have a limit on the width to thickness ratio. And see where it says 0.56 square root of E over Fy? Everybody see that? So what we do when we do a column analysis is before we start plugging into these equations, what we do is we say, okay, let's compute 0.56 square root of E over Fy, and let's compare that to how slender the flange actually is. So this is a measure of how slender the flange actually is. This is my limit. And as long as my slenderness is less than the limit, I'm good. Because if the slenderness is greater than the limit, that would mean I'd have a slender flange, and these equations really wouldn't work on their own. Does that make sense? Yes?
How do stiffeners change all of that?
Stiffeners. Are you talking about vertical stiffeners across the... That's a great question. They don't. The stiffeners perform a different function. Stiffeners, if you're talking about longitudinal stiffeners, that's a different story. But transverse stiffeners along the span are intended to increase the beam's shear capacity. Now, if you have like an I-beam and you had, let's say, like a stiffener going this way, well, then it could change that. But that becomes a little bit of an involved analysis, and it's something we never really do in practice anyways. We do have shear stiffeners, though, but it wouldn't affect this at all.
Okay.
That's a great question. Does this make sense? Okay. That's for the flange. This is for the web. And if the section fails these limits, we say that they're slender elements. Now, let me show you something. I want everybody now to go to just the wide flange section. So like any, I don't know, table 1-1. Give me the properties for like a W10/49 or something like that. Now, one of the things that you will notice is, so let's just look at a W10/49. It doesn't matter. If you look at the W10/49, look to the page on the right. And if you look on the column above, you see where it says compact section criteria? And see what it lists? It says BF over 2TF and H over TW. So the spec already lists for you the flange slenderness and the web slenderness. You don't need to go and compute that. Now, why is it BF over 2TF? because I'm only considering half the flange. So that's why it's BF over 2TF, because I'm only considering that limit over there on the left, or that half that flange. And so if you notice, you'll see that those are already sort of computed for you. Now, let me be clear. What if you fail these limits over here on the right? Like, what if your flange is too slender? That does not mean that the column explodes upon the putting a feather on it. All that means is that if you fail these limits, then these equations over here on the left just don't work, and you have to use different equations. Those equations over on the left board are from section E3. Look at the title of section E3. Flexural buckling of members without slender elements. Section E7, members with slender elements. So whether or not you fail this limit over here on the right tells you whether or not your section contains slender elements or not. Make sense? Now, let me show you something else. We're on the page W10 by 49. I want you to look at the very bottom on the left. Does anybody see a footnote on the bottom left? One that has a little C on it? Tell me what the C section means. What does it say? Let me read it out for me.
Shape is slender for compression, with the yield stress being 50 KSI.
So here's what that means. Let's take a W10 by 17. Does everybody see the W10 by 17? Does everybody see it has a little C? What that means is this. You check these limits over here on the right, they're going to fail. Somebody asked me a while back what those little footnotes mean. That's what they mean. That if you check the limits for compression for that section, it's going to fail. So here's where I'm going to get to be a little bit of a stickler. I'm going to make you check these elements for every section. There's a reason why. It's not because I'm trying to make you do extra work. When you go into bridge land and you're looking at, let's say, like tailoring the size of a plate girder, you really do need to check these limits, because unlike a rolled shape, you're going to be changing the size of the flange and the thickness of the web and the depth of the web. And so when you're in plate girder land, these limits are not just, oh, they're going to work. No, they very well may fail because you're tweaking the sizes. You really need to know where those limits are coming from and know whether or not your section meets those limits or not. So I am going to make you check those limits for every problem that we do. Not because I'm trying to be a jerk, but because if you all go into bridge lane, you're going to do these calcs all the time. So, everybody okay with that? Yes?
Is that only if the yield stress is 15?
That's a great question, and the answer to that is yes for those notes. So, if I gave you one that was 60 KSI, the ones that don't have the footnotes might still fail because it's a different yield stress. It's a great point. Great point. Sound good? Now, so here's sort of your procedure for analysis. If I give you a column and I ask you to determine how strong the column is, the very first thing you should do is this. Ask, is your flange slenderness less than or equal to this limit? And is your web slenderness less than or equal to this limit? If that is the case, then you're good to go using section E3. If not, you got to use section E7. We might talk about E7 at the very, very end, but most wide flange columns, that isn't going to be a problem. I'm still going to make you check it, but it's probably not going to be a problem for what we do in here. Now, once you verify that the section is compact, there's actually 3 different ways to compute the capacity. I have a typo here. I said table 422. I'm sorry, it used to be table 422. It's table 414. I apologize for that. That's table 4. Now, if you have determined that your column is in fact compact, that it does not contain slender elements, there are actually 3 ways to determine the capacity. The first is to just use these equations. The second is to use one of the 2 design aids in the manual, and we'll go through each of these in detail. So the first is just to use this. So just so you're aware, we have this one example we're going to do 3 times, and it's going to be looking at each of these different methods. Now, I know I keep harping on before we start doing our example, but this is probably, if there's any one thing about columns that becomes complicated, it's the slenderness. Now, if ever you look at a W section, there's always 2 radii of gyration. There's an Rx and an Ry. the radius of gyration about the x-axis and the radius of gyration about the y-axis. And Rx is always bigger than Ry. We always call the x-axis the strong axis. Like if I take this, it is easier to bend it about the weak axis. It's easier to bend it this way than it is to bend it this way. I mean, you can feel it if you bend it. It's kind of flimsy this way, but this way it's got some oomph to it, okay? Well, the question is, do you ever have to check the strong axis? And the answer is yes. Let's take a look at this column. So this column, I've got bracing about the y-axis, but not about the x-axis. So if you look at the x-axis, this column is completely unbraced for a length of 35 feet. But for the y-axis, I actually have different sections. I have a section here that's 10 foot long, a section here that's 15 foot long, and another section here that's 10 foot long. So I actually have 4 different KL over R values that I have to compute. Which one do I use in computing the capacity? Whichever's biggest. Bigger slenderness means lower capacity. Whichever has the biggest KL over R, that's the one that governs. Okay? Because again, just because Rx is bigger than Ry, it doesn't mean that the KL over R isn't the case. So make sure you always check the KL over R for each axis. In fact, we're going to take this column, and so what you would do with this column is you would actually split it up into 2 different analysis models, one for the x-axis and one for the y-axis. In fact, why don't we go ahead and just do that example. So I want to analyze this column. We're going to assume it's a W14 by 90 made out of grade 50 steel. And I've got the strong axis bracing on the left and the weak axis bracing on the right. Now I'll go ahead and prepare you. We're going to be doing a lot of flipping back and forth in the manual here. So there's going to be a lot of parameters that we look up. So just be aware of that. Okay. Give me a sec. Oh, I didn't open my notes. Okay. So, first off, we're dealing with a W14 by 90. We were told that Fy is 50 KSI. So I need a couple properties from this section to be able to do this problem. The first thing that I need are some section properties. So I'll go ahead and tell you I need AG, RX, RY, and I need my flange slenderness, which is BF over 2TF. And I need my web slenderness, which is H over TW. So help me out. What's the gross area of this column?
26.5.
26.5. All right, what about RX and RY?
RX is 6.14 and RY is 3.7.
Okay. And lastly, the compact section criteria, the BF or the BF over 2TF and the H over TW. It's on the next page. 10.2, 25.9. Now, what are the units of the compact section criteria? There are none. It's a BF over 2TF, inches over inches. They're unitless. Slenderness values are always unitless, so just something to keep in mind. All right, everybody with me on this? All right, so let me. What does it say?
It says shape exceeds compact limit for flexion.
Ah, that's a great question. So the problem says the shape exceeds the compact limit for what? flexure. So what that means is if we were looking at this section as if it was a beam, we would fail the section criteria. But this isn't a beam, it's a column. Okay, this is a great question. All right, does that make sense? Okay, now, the first thing we're going to do is check these. Okay, so let's do that. Let's start off here. I'm actually going to move these up here. I have a little bit more room. Okay, so we're going to check local buckling first. So the first thing, let's look at RF for flange. So 0.56 square root of E over Fy, 0.56 we have that. Let's see what we get. $13.49. Do I have a second on that?
Yes.
Okay. Now, sometimes students get a little confused about this. I want to make sure this is clear. Okay. Lambda RF is 13.49. Lambda F is 10.2. This is the limit. This is the actual slenderness. Remember, as slenderness values get higher, the flange is going to get more and more flimsy. Okay? So if the slenderness was larger than this, we would have a slender element. But we don't. So because this is less than that, so because lambda F is less than lambda RF, we have a compact flange. Does that make sense?
And that just means we can use these equations.
Yes, but we're not done. We got to do E7. Again, if you fail this limit, it does not mean that the column will explode if you put a feather on it. It just means that those equations are wrong, or at least are not good enough by themselves. So 1.49 E over Fy. Anybody have an answer for this one?
35.9.
Okay, so, and then this is 25.9. So what's going on here? So this is the measure. This is the limit. This is the maximum slenderness limit before we have to declare the web slender. But this is how slender it actually is. So do we have a compact web or a slender web? Compact web. There we go. So we have lambda W less than lambda RW, compact web. And so all this means is that section E3 is applicable. That's all that means is section E3 is applicable, not section E7. So we can still use these expressions. Everybody good? Now, before we start using these expressions though, let's take a look at this. So, in order to use these expressions, I mean, the kicker is figuring out what's going on with the slenderness. That's the issue. Okay, so let's take a look at that. Come on. We're getting there. Let's get that. Okay. So let's take a look at the bracing situation. So first off, I want to explain these symbols. So this is just saying that the column's facing that way. This is saying the column's facing this way. So what's going on here, if I look at the column like that, what do I see? I see the flanges and the web. Whereas if I look at the column this way, see these little dashed lines right there? That's the web through here. So does that make sense? So that's what these symbols are indicating, is which way the column's facing. So this would indicate the column is buckling sort of out like that. So that's strong axis buckling, and this is weak axis buckling. So that's why the columns are, or the symbols are the way they are. Does that make sense? Okay. Now, if that makes sense, we've got everything that we need except for one thing. I've got my R value. So when I say slenderness, I mean KL over R. Well, I know my R values. I just looked them up. I can get the lengths right here. That sort of means we need to look at K values. So where do we look up K values? Told you you're going to be turning back and forth a good bit in this. So if you haven't tabbed that, go ahead and do so. That's way in the gray section of the manual, 16.1-570.
Ooh. Way back here.
16.1. All right. So let's start off with the x-axis. So this is a fixed support. That is a pin support. So if I have a column that's fixed pin, help me out. What is K for this segment going to be? I told you, we're going to have a lot of tabs here. If you haven't already tabbed stuff, it's time to start tabbing. So help me out. What's the K value going to be if I have a fixed pin situation?
0.8.
0.8. Remember, you do not use the theoretical value. You use the recommended value for design. The theoretical value, I believe, is 0.7, right? So this is 0.8. Okay? Now, for this segment, we actually have 3 different separate segments. So what I'm going to do is I'm going to call this KY1, KY2, KY3. Now, let's look at KY3 first. Is KY3 any different than KX? I mean, what's going on? The bottom is fixed. The top is pin. So what's the K value for that segment? 0.8. Now, if this is 0.8, what is the K value for the other 2 segments? It's 1, because they're both pin-pin. So this is 1, and that's 1. Sound good? So here's the way I do this. So we have K, so this is 0.8. 1, 1, 1. Now let's look at the length. How long is the X segment? How long is that?
35.
35.
Feet.
Is Y three supposed to be?
Oh, that's supposed to be 3.8, thank you. This is 0.8, thank you. Now, you said that L was 35 feet, but, hold on, we're going to take a radius of gyration in inches and combine it with a length in feet. It's not going to work out. So 35 feet is how many inches?
420.
420 inches. So this is 420 inches. All right. And for the remaining segments, I got 10, 15, 10. I need to do the same thing. Okay? This is not 10 feet, but 120 inches. This is not 15 feet, but 180 inches. This isn't 10 feet, but 120 inches. Again, consistent units. Lastly, we have the R values. And so this is about the x-axis. These three are about the y. So I'm getting the R values that I looked up before, 6.14, 3.7. And so KL over R. We're not going to have time after this, so we're just going to call it. So, after this. So, give me the first one. Let's say like 2 decimal places, probably close enough.
54.72.
Okay, what about the next one?
32.42.
Next one?
$48.65.
And the last one. Wait, what?
25.
Say it again?
25.94.
Okay. Yeah, that's what I got. Now, I want everybody to pay attention to this and we're going to call it. First off, which is the highest value? The X one. So this column is actually going to buckle about its strong axis before it buckles about the weak axis. It may have a larger moment of inertia and a larger radius of gyration about the strong axis, but because the strong axis is unbraced for a distance of 35 feet, it's going to buckle first. So that would be my first point. My second point is we actually wasted our time a little bit because if you look at the y-axis, I have 3 segments. But look at the center segment. The center segment has the largest K value and simultaneously the largest length. So by observation, this was going to have the largest slenderness of all 3 of these. So if you wanted, you could have just computed the x-axis and then just that one for the y-axis. For posterity, I went ahead and did all of them, but, you know, upon observation, really all you need to do is this one. So KL over R is 54.72. Now, we do not have time to finish this problem. We'll do that next time, where we take this value and then compute the capacity. Quite frankly, you could do that on your own. Just compute that, figure out which one, if you're doing here and here, compute the capacity. What we'll do is do that, and then we'll do it 2 more times using some of the more refined design aids, and we'll see how the capacity matches up. Sound good?